Well, you'll be happy to know that just as we use the concept of derivative to help in our analysis of functions of one variable, as we did in Calculus 1, using partial derivatives to find, or using derivatives to find maximum points and minimum points and rates of change and concavity even, we can use partial derivatives. You might recall we did a little bit of work with partial derivative at the last video in the last section, so you'll be happy to know that we can use partial derivatives to analyze functions of two variables in a similar fashion. I knew you'd be happy to know that. So, here are the definitions of partial derivatives of functions of two variables. If z is some function of x and y, then the first partial derivative with respect to x, or you could say the first partial, are notated f sub x and f sub y, and you can see why we can't use prime, because you have to be specific about the variable. So f sub x of xy is the limit as delta x approaches 0 of f of x plus delta xy minus f of xy over delta x. Notice the similarity between this definition and the definition of derivative of a function of one variable. Similarly, the function fy is defined limit as delta y approaches 0 of f of xy plus delta y minus f of xy over delta y, and we can calculate such a thing just as we did in Calculus 1 from the definition. We're going to use this example, x squared plus 2xy plus y squared, and find its partial derivative with respect to x. So that would be the limit as delta x approaches 0 of x plus delta x squared plus 2x plus delta xy, so 2x plus delta xy plus y squared minus f of xy, which is just this, all that over delta x. Now, notice that we would have x squared plus 2x delta x plus delta x squared plus 2xy plus 2 delta xy plus y squared minus x squared minus 2xy minus y squared. What happens is this x squared and this negative x squared cancel out. We have a 2x delta x that doesn't cancel out. We have 2xy, which does cancel out with this negative 2xy over here. We have a 2 delta xy, which doesn't cancel out. We have a delta x squared that doesn't cancel out. We have this y squared, but it also cancels out with the y squared over here. So this is what our expression simplifies to. But now I want you to notice that you could factor a delta x out of the numerator and cancel it with a delta x in the denominator. So I probably should have typed limit as delta x goes to 0 here, so you can see that this delta x is 0. So it's just 2x plus 2y. So what we've discovered is the partial derivative of this function with respect to x is 2x plus 2y. A few things to note. If you took the derivative of this and y was a constant, it would be 2x plus 2y plus 0. So that's exactly what you do. You treat the y variable as a constant. And so the partial derivative with respect to y can be found in a similar fashion. And let's say, unless I dictate otherwise, from now on, actually you might want to try to do this as an exercise, show that the partial derivative with respect to y is also 2x plus 2y, and then from now on we'll say you'll be able to find derivatives using the rules, not the definition. I knew that would make you happy.